So we have done this comparative statics in the open city model, where we fixed the utility level and we would get then the population size. Now, please stop with the application, the Java application, and let's move. Well, we don't have access on this application to the closed city model, which is a bit more difficult to solve. But we can guess what happens when you change the parameter in the closed city model. So we discussed it before. What's the difference then in comparative statics? So comparative statics is what we have been doing so far, changing one parameter at a time and looking at the outcome and the results. So what is the difference if you change, for instance, the transport cost between what we have been doing in the open city and in the closed city model? So imagine now you increase the transport cost in the closed city model. What is the effect? So in the open city model, we said what changes is the population size. You increase the cost, then you decrease the population size. There are less people moving in from outside of the world, outside of the city. What happens in the closed city model?
Even the density gets higher. If the number of people don't change.
Yeah, exactly.
The city shortens, the density.
Exactly, you don't change the number of people, the density would get higher in the center, the city would be a bit smaller. What happens in for the utility of people, the economic welfare? It decreases, yeah, they are less happy because their costs are increasing. So, the conclusion is it's important to consider both frameworks, because if you imagine that in a real city, you have the transport cost increasing. Imagine that, for instance, you have no more oil because peak oil is past. Then cars have to pay, car drivers have to pay a lot more to drive to the city center. What happens to a real city in this case? So my guess would be that a bit of what happens in the both frameworks would happen. So you would both have the economic welfare of people, which would decrease because they have their costs increasing. And also maybe some people moving to the outside of the city. So both something of a mix between closed and open city models. So I mentioned this because the models we are going to look afterwards, they will be either in one framework or the other. So you won't get both answers at the same time. But for a real situation, I think it's quite important to remember that the choice of one or the other framework is really influencing the answers you get to your questions, to your research questions. Is that clear? Does anyone have any question about this comparative statics? No? The influence of parameters, you begin to have an intuition of how this model works and what are the influences of these parameters? Okay. So now I'm going to speak in this next part about empirics and urban economics. So both from the economic theory side and also from my own perspective, let's say. So just to start with the economic literature. So when you look at empirical papers linked with this urban economic literature, you have the impression that the model works perfectly, actually. So that it's really extremely accurately describing what the city looks like, and it's explaining everything about the urban housing market. So for example, I mentioned this paper which is a nice paper, I think by McGrath in 2005, More Evidence on the Spatial Scale of Cities. So if you want, you can have a look. I put it on Moodle, but I will summarize it quickly here. So this guy looks at the area of 30 American cities over 5 decades, so between 1950 and 1990, and he has one time point at each decade. And he does a statistical analysis of how he also has for each of those cities, its population, income, the average income, transport cost, agricultural rents at each of these time points. So, and he does a statistical analysis to see how the area, he also has access to the area of these cities, how the area evolves with all these parameters. And his conclusions are the following. So the area evolves just as you would expect it to evolve from the model we have seen so far, so from this comparative statics. So when you increase the population size, the area of the cities tend to increase. You increase income, the area tends to increase also. That's everything we saw in these models, in the simulations you did just now. When you increase transport costs, the area of the city tends to decrease. And when you increase agriculture rent, the area tends also to decrease. Okay? And this is quite representative of what you see in the economic literature when you look at empirical facts for this urban economic model, which we are studying now. So just very quickly, some other examples of papers which have a more or less the same message. So in 2010 from Alfeld, the paper is named "If Alonso Was Right, Modeling Accessibility and Explaining the Residential Land Gradient." And if you look, the conclusion is yes, Alonso is right. So it's Alonso's model. So yes, the model is working. And this other paper from 2008, the Mills-Moos model of urban spatial structure surviving the test of time, question mark. So Mills-Moos is more or less the following of Alonso, so it's really the same model. And the conclusion is also, yes, it survives the test of time. This model is working with it really corresponds to real cities. But my point is that what these people are doing, the kind of analysis they are doing, is not deep enough, in my opinion. So I will go a bit further. These people are doing a statistical analysis of, for instance, looking at how the urban area evolves with parameters. But what they never do is to check how these curves, which we have obtained so far, for instance, the density curve, the rent curve, could be fictive to actual empirical data. There are very few, almost no papers which do that. So there are some attempts. That's what I call a calibration. So calibrating the curves you obtain on real data. There are some attempts. For instance, this paper which I present here, the influence of public open space on urban spatial structure. It's also an interesting paper, but if you look at it in the paper, what they do is, in my opinion, quite unsatisfactory because, well, they have only one city, so they only study one city. They don't see if the model can reproduce many cities, many different cities. The city has only 2,000 inhabitants, so you have to imagine this kind of model which we have, where everyone is commuting to the central business district of a city of 2,000 inhabitants. Well, I don't know what the central business district of a city of 2,000 inhabitants looks like, but it's probably fairly small. So it's not really the kind of model you would want to fit on such a city. And they don't really compare empirically the rent curve and the density curves with the theoretical results. But at least they try to give a value for all parameters. For instance, the income, they take the average income of the city, the transport cost, etc. So they give transport cost, a cost per kilometer, etc. That's already something. Most papers just do theoretical work with no comparison to empirics whatsoever. Okay, so I will discuss just next a few problems which this model has when you compare it to real cities, let's say. So first about land use. I don't know if you were very well aware of this, but so far we have considered that all agents are living on the ground, so there is no building construction, and the whole of space is used for housing. We have no other land use except outside of the city we have agriculture, but inside the city it's only housing. While in real cities, as you can imagine, it's not like this. So this is what I'm presenting on those figures. Well, I advise you to look also on your screen at the presentation because it's probably too small on the board. But so if you look at real cities, actually, a large part of land in cities is not used for housing and is not even artificial. So this is empirical data from several capital cities in Europe. And you see the share of land which is artificial between 0 and 1 as a function of the distance to the center in kilometer on the figure of the left. So you have these two first curves. green and purple for London and Paris, the two biggest cities in Europe, so the two biggest urban areas at least. So it's roughly 12 million inhabitants. And then you have three smaller ones, Warsaw, Budapest, and Lisbon, which have roughly 2.5 million inhabitants in their urban areas. So the numbers given in the legends are the population sizes of those cities. And then you have three even smaller ones, Tallinn, Ljubljana, and Luxembourg, roughly 500,000 inhabitants. And you see that, so very close to the center, most of the land is artificial, almost 100%. But this falls quite quickly. It falls actually more or less exponentially. And actually, I can mention that for larger cities, it's more slowly than for bigger ones, for smaller ones. Sorry. So for small cities, you have a very sharp decrease in the land use for which is artificial, and for large cities, it decreases more or less in the same way, but more slowly. So what I will mention it. So this is a work which is not published yet, but which is an interesting fact. You can try to see if their shapes are exactly the same, exactly comparable between different scales of city. Are small cities similar to large ones? So what you can do for this is to rescale the horizontal axis, so the distance to the center. That's what I do on the left, the figure on the right. Sorry. So it's exactly the same data for the same cities, except that the horizontal axis is not anymore the real distance. It's the distance which is rescaled by a factor which I call the Kc. And this Kc is just the square root of the city population, the considered city population, and then I divide by the population of London, so that these factors for London is 1. So it doesn't change London, it doesn't change Paris, because Paris has more or less the same population as London, it's also 1. But for all other cities, you can see that these factors are bigger and bigger. So 1 for London and Paris, 2 more or less for Warsaw, Budapest, and Lisbon, and then more or less 5 for Tallinn, Ljubljana, and Luxembourg. And what you see on this figure is that all curves are really, really similar to each other. So this is what you call a scaling law. So all cities are quite similar to each other, but you need to rescale the distance. So in terms of land use. And I could just mention that there's a small hole in the center in Lisbon, which can be a bit strange, but if you know Lisbon, it has the Tagus River estuary right in the city center, and also there's the ocean very, very close. So a large part of land is used is actually water. So that's why there's this hole. Okay, so just to mention that there's a problem of land use in this urban economic model. So land is not actually artificial, and if you look at the land which is used for housing, actually, it has more or less the same shape as the one which is shown on the artificial land shown on these two graphs. It's just that instead of starting at 100%, it starts more or less at 50%. So in the center of European cities, you have more or less 50% of land which is used for housing, and then it decreases again exponentially with the same scaling laws. Okay? So that's one problem of this urban economic model. It doesn't describe land use in an accurate way. Any question about that? Fine? Okay, so another problem. How to determine the city fringe. So for a real city, where do you put this city fringe? Where do you measure the agricultural rent? If you suppose in this model that you have at the border of the city, land is used for agriculture, well, after the border. If you look at real cities, actually, the city fringe is not really decided by a competition for land between households and agriculture. It's a bit more complex than this. So I will show you quickly maps of real cities. This is Paris, for instance. So you have here the intra-city of Paris, and in yellow you see agricultural plots, and well, there are agricultural spaces even quite close to the city center. So if you look at the whole urban area, it's of course much, much bigger than this, but there's already agriculture somewhere here. So where would you measure your agricultural rent? So it doesn't make so much sense to say that at the border of the city that this competition between agriculture, this sharp competition, sharp transition from purely artificial housing and then agriculture. Same thing in the next slide for Rouen, a much smaller city. Well, you see that there's agriculture already very close to the city center in many different places. And the urban area is, of course, much bigger than this. So, again, where to place the city fringe? Where do you measure the agricultural rent? So that's one more problem of this urban economic model. One more way where it's not really realistic. Another one is the location of employment. So if you remember, we suppose that all employment is in the city center, in the central business district. So if you look at real cities, it's not really the case. So there have been some extensions of this model. We will speak about it later in the afternoon also. Instead of having this monocentric city model, so with just one center, the center can be actually also just a punctual a point like the one we have studied so far, or even give it a certain extension, so it's occupying some space because you expect it, of course, to occupy some space. This is the case, for instance, in London. If you look in the city of London, the financial center, etc., there's no one living there. It's only employment. So there are models like this, and there are even models with multiple centers. So this polycentric city model. We will speak about it later in the afternoon. And if you look in real cities, actually the job locations are quite dispersed. That's the reality. This punctual center is quite far away from reality. Okay. Okay, there's also a problem regarding transport and commuting. So in this model, what we have is people moving from radially from where they live to the city center and commuting there every day. There have been people who tried to compare empirical commuting to the theoretical one predicted by the model. And for instance, there was a big discussion in the economic literature on this paper called Wasteful Commuting in 1982. And the question asked was the following: so, can the monocentric model predict the actual commute lengths in urban areas? And the answer was no. So the commuting length, which was seen empirically, was, I think, something like 8 times bigger than the one you expect from the model. And well, the reason for this, which were proposed in this paper, there were several ones actually. So they say what I just said before: the job locations are dispersed, so people are not just radially going to the center; they go a bit everywhere in space. There are moving costs in reality. Even we don't have such in the model. So, but in reality, if you change jobs, you are not automatically moving your residential location because it's not easy. It's costly in time, in energy, etc. There are 2 workers households, of course, and even with children, etc. So more constraints. So if your partner is working in a certain place and you in the other, maybe you would try to locate between both employment locations. So your commute would be a bit longer because of that. And for instance, also some people are making a trade-off between commuting for work and other trips. For instance, going shopping on the way to work or dropping kids at school, etc. So this influences also their commuting trip and their residential location. Okay, so this is also one more aspect of this model which is quite unrealistic. Okay, what do economists usually do, and then geographers also actually, when they see all these problems when you compare this simple model to reality? Well, the answer is usually the following: if a simple model does not work, then a more complex one will. So if your model is not in agreement with reality, then you just need to make it more complex. And so there have been lots of works which have been doing this on this model. So For instance, I spoke about polycentric city model, so people have added more centers to account for the fact that not all employment is in the CBD. Models with mixed land use, so mixing agriculture, for instance, with housing in peri-urban areas, or having gardens, which a surface which is used for gardens or for roads, and this would enter also the utility of households, etc. There's a famous extension of this model which is attributed to MOOC, which considers housing construction. So there's a housing construction industry which builds houses, buildings using land and capital, etc. But of course, this approach has many drawbacks. So if you have more parameters, if you have a more complex model, you have more parameters. And these parameters might be difficult, are probably difficult to measure, to compare to reality, to empirical data. We will speak about it in more detail just afterwards. They may be difficult to solve, these models, more difficult, and also more difficult to explore, even. You can even have, in some cases, several equilibria. So we had only one solution to our model. But there are more complex models where you have several equilibria, and then the path you choose, the dynamics you have to will decide which equilibrium you go to. So there's this path dependency effect in some models. By becoming more complex, they become also more less explanatory and less predictive. I will argue a bit more on this later. And also this whole approach has the main problem. I think that it's impossible to prove wrong. When your model doesn't agree with reality, you just say, oh, it's not complex enough, so let's add one more parameter or two more, and then you will make it more complex. And at some point, you always manage to keep in line with reality. So let me speak about it just a bit more. So this is really, I said I'm a physicist by training, so this is really a physicist's approach to geography. So it's not really mainstream geography, but yeah, that's really standard for physicists. Actually, the saying, I guess, among geographers is that physicists are really scared as soon as the model has more than 3 parameters. They are, oh, what's happening? I don't know where I am. So the reason why is linked to this famous quote. Well, famous at least in physics. I don't know if you heard about it, from John von Neumann. And the quote says, "With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk." So I will just say a few more words about this John von Neumann, because he was a very interesting person. Actually, I don't know if you noticed, but when Justin presented you the theory before, he spoke about a theorem by von Neumann. So he was actually a mathematician, but he made really important contributions in mathematics, in physics, in economics, in computer science also. If you remember maybe the von Neumann neighborhood in NetLogo, for instance. So he was one of the people who built actually the first computers and who invented cellular automata. So he's really someone who grounded many of the things we are studying now. He's also one of the people who built the atomic bomb. And he was really influential in this thing. And yeah, he was really considered a genius by many people. He was already a prodigy child, speaking many languages, having a crazy memory, able to remember phone books, etc. Well, okay, so that's for the people part about von Neumann. And the other figure is just that some people have tried actually this. This saying is so famous that people have tried to just fit an elephant with the 4 parameters. And they managed to. And with the 5th parameters, they even managed to move the trunk. So that's the. But yeah, this is just for the joke. So what he meant, I think, with this quote, is that if you have too many parameters in your model, you have too much freedom. You can make it say anything you want. So it's possible for you to fit any real data if you have enough freedom within your model. Is this clear? So actually, when you have empirical data, it's like constraining your model. It decreases your freedom. So you need to get more data to constrain your problem more. And this is really why physicists are scared of models with more than 3-4 parameters. I should note also that even simple models, that's what I was discussing just before, so even a simple model like the Alonso model can be quite difficult to compare to reality. So if you want to measure for a real city the transport cost, imagine how do you measure a transport cost per unit distance? Which kind of data can you get to measure this cost? Is it just a monetary cost, or do you have to take into account a time cost? And then how do you measure a time cost? How much people are willing to pay for a shorter trip or a longer one, etc. So that's really complicated, and it's just a simple model. So imagine with a model with tons of parameters, complicated ones. So a kind of small conclusion of this is this killer question, which I put in the end, which you can use, I think, almost in any presentation you will get in those 2 weeks. So you ask the presenter, how many free parameters does your model have? And then if it's like 4 or 5, then you know from Neumann that it's possible to fit even an elephant with it. So you understand the idea? So yeah, as long as you have a lot of freedom, then you can fit anything. Okay, I just want to say a bit more about this, because we are anyway going to study models which have more than 3 or 4 parameters. Already Alonso, we were looking at 4 of them, and well, the advantage with this model of Alonso is that we have an analytical solution. So with an equation, you can already look, just by looking at the equation, you can know how things vary. But if you have a simulation models with 4 parameters, you have to explore the outcomes of the models. And this is already difficult, so that's what I'm going to discuss now. So if you have a simulation model with a few parameters, you need to explore the parameter space to see the results of the model. So I will explain why the usual exploration which people make, which is called sensitivity analysis, is quite superficial. So this sensitivity analysis, has everyone heard about sensitivity analysis already? Who hasn't actually? It's okay to say I haven't. You haven't? Okay. So sensitivity analysis means you look at the outcomes of your model by changing each parameter one by one. You change one and you don't change the others. It's more or less what we did actually when we said we were doing comparative statics. That's the name of the economists actually. So you change one parameter, you don't change the others. And that's what people usually do for their model. You change just one parameter and you don't change the others. So suppose you have 3 parameters, and then that you want to explore 10 values for each of those parameters. So those 3 parameters, we would call them x, y, and z, for instance, and I represent them in this 3-dimensional space, x, y, z. So if you want to explore your model fully, you have to choose every combination of the 3 parameters with 10 values for each. So if you do one simulation per combination of values, it gives you 1,000 simulation, 10 to the 3. The sensitive analysis in comparison is very simple. You just change each parameter separately. So you have just 3 times 10 simulations to do. 10 simulations per parameter. But what you explore is very different. With the sensitivity analysis, what you explore is just the axis that I've drawn. So if you change the z parameter, you would move on this vertical axis, move on the y and the x axis, but the rest of the space is left unexplored. You don't know what happens in all the rest of the space. With the complete exploration, you would know everything that happens in your model. And of course, for the sensitive analysis, there's a very important point, which is the origin, this O here. The way you choose it, usually people don't say how they choose it because it's quite arbitrary. But of course, it influences what you are looking at because you look really closely to this point, but the rest, you don't know what happens in the rest of the space. Okay? I'm sure there are questions, no? One question? Easy? Mainly happy, no? Really no? Okay, so, sorry, I'm going to continue a bit on this. Sometimes some people attempt to change parameters 2 by 2 instead of just changing 1 by 1. What does it mean to change parameters 2 by 2? It means you explore planes instead of exploring lines. So for instance, if you change x and z together, you explore a vertical plane, which is the plane where this board is. And there are three such planes in if you have three parameters, so the xz, xy, and yz. Okay? So the full exploration, as I said, is to have 10 to the 3 simulations. The sensitivity analysis is 3 times 10, so 30 simulations. And for each of these planes, actually, you have 10 times 10 simulations. There are 2 dimensions. So it's 100 simulations, and you have 3 planes, so it's 3 times 100 simulations. Okay, just to give you an idea. So already, moving all parameters 2 by 2 is already usually really too demanding, and one does it. So, but this is just a very simple model. It has only 3 parameters. So let's do it on the next slide. Let's try to guess what it gives when you have more than 3 parameters or less. So try to fill actually those question marks. Please don't look at the next slide where the answers are. So you have let's say 5 minutes to just try to fill this table. Find what are the numbers of simulations for each of these question marks. Deuxième ligne, c'est un peu plus compliqué. Ah, d'accord.
Mais ouais, tout à l'heure, tu as dit tout by two, c'était 2 fois 6. C'était 3 fois 6.
Ouais, c'est ça. C'est ça, la constitution. Quand il y a plus de 3 paramètres. En fait, quand tu fais 2 paramètres, il n'y a que 2 paramètres d'ailleurs. Il n'y en a que 2 des paramètres, donc il n'y a qu'une manière de choisir les 2 paramètres. Il n'y a que 100 simulations possibles. D'ailleurs, c'est la même chose, c'est simple. Parce que 2 paramètres, c'est plus simple. Il n'y a que 2 paramètres, tu veux les faire évoluer 2 par 2. Tu fais 100 simulations, il n'y a qu'une seule combinaison par 2. Donc en tout, il y a 100 simulations possibles. C'est un peu plus simple de faire multiplier par 100 par 3 manières de choisir les 2 paramètres qu'on veut faire varier.
Ouais, on fait toujours varier les paramètres de base.
Voilà. Et du coup, dans le cas de la 4, combien de manières de choisir les 2
en fait, une fois. Il y a 2 dans l'ensemble. Je regarde, c'est puissance 4. C'est 8 ou 16?
Okay, let's say you have all finished. Let's look at the answers then on the next slide. So actually the first and the last lines are quite simple. So the first line is just you multiply the number of parameters by 10. For each of your parameters, you do 10 simulations to look at the outcomes of the model. For the full exploration, so you have to look at all values for all parameters. So each time you add a new parameter, you multiply the simulations you had done before by 10. The 10 new values which you want to explore. So it's 10 to the number of parameters. So for n, it's 10 to the n, and in this case, it's just 10 times n. Okay, there was a slight difficulty with if you look at parameters 2 by 2. So if you have only 2 parameters, there's only one way to choose those 2 parameters. You look at them 2 by 2, so you have you do your 10 by 10 100 simulation. So it's those two numbers are actually the same. Yeah. Then with 3 parameters, we said there was 3 possible planes in the 3-dimensional space. You remember? So there are 3 ways to choose your couple of 2 parameters. So you use x, y, y, z, and x, z, and then you have all combinations. And actually, if you have 4, 5, etc., the number of parameters is changing. So you have 6 combinations if you have 4 parameters. You have 10 if you have 5. And in general, it's this combinatorial number. So the number of ways to choose 2 parameters among n. So actually, this is equal to n minus 1 over 2. If you remember, well, it's not really important. Sorry. So just to conclude on this is linear. So it's just 10 times n. It's always possible. Even if you have 10 parameters, while you have to do 100 simulations, it's bothersome, but you can do it. But you have this very, very superficial exploration of the parameter space, the one we described before, just looking at the lines. The full exploration is extremely difficult. So even with, 4 parameters, you have already 10,000 simulations to do. And this is also supposing that for one set of parameters, you just need 1 simulation. But if you imagine a model where you have some stochasticity, some randomness, then you might need to do more simulations just for one set of parameters, like 10, and then you do statistics. So this would multiply all your numbers here by another factor. So really, this is a big problem. If you want to explore the parameter space fully, it grows exponentially. So the n is an exponent. So that's an exponential growth. Is it clear? And then, I just mentioned the 2 by 2 to see the difficulty, but already 2 by 2 is much more complex than 1 by 1 because this is actually quadratic in n. So it grows really much faster than linearly. And usually people just do this sensitivity analysis. So this is something you can have in mind for, I think, most of the models you will be presenting in those 2 weeks, actually. So there's this problem. When you have many parameters, you can't really explore your model fully. And that's why we physicists are scared of this. Okay. And the conclusion, of course, is to be parsimonious, the parsimony principle. You want to avoid being trapped in this frightening complexity and being lost in a parameter space you can't explore. Okay? I will say just one more thing about this, because there's a very related problem in rather in data analysis, in statistics. So if you have data, I took this image from Wikipedia. So you have data. These are the red crosses, and you want to fit a model inside. So let's say you choose a polynomial model, and you have to choose which degree of polynomial you want to use. So this would be degree 0. You just draw a horizontal line at the average, and then you can do degree 1. So you fit a straight line, degree 2, etc. And then when you increase the degree, of course you increase the R square, so you come closer and closer to 1. And actually, you can see when you reach degree 9, that, chi square is 0, R square is 1, you go exactly through all points. But this is actually non-informative at all because there is a theorem which tells you if you have 10 points, then there is one polynomial which goes of degree 9 which goes through all points. So already a theorem is telling you that this polynomial exists. To have it is no information. So any n points can be fitted by a n-1 polynomial, exactly. So this gives you no information. So you have to choose what polynomial is more informative. So I would go rather, for instance, in this case, for a straight line or something like this, but really keeping a few parameters, as few as possible to stay informative. So this problem in statistical analysis is called overfitting. So if you have too many parameters, too much freedom again, then you can fit anything, even an elephant. Is this clear? Okay, it's quite related to this problem of a large parameter space. Okay, well, I need to... Okay, is there a question about... yes?
Yeah, do you use full exploration to do calibration? Or?
Well, one way to calibrate a model would be to do full exploration, but we saw that even with very few parameters, it's impossible. So if you have a simulation model and you want to calibrate it, so I think what people do most of the time is to try and go to change parameters one by one, if you want, and try to find the change which gives you, makes the model closer to the data, if you want. So that would be kind of a gradient descent or something like this. But there are many methods, or simulated annealing, etc. There are many methods to do this. But usually you just follow a simple path through your parameter space, which just leads you closer to the data. Does it make sense? Yeah? Another question? No? Okay, we have only spoken about equilibrium models so far. There was one equilibrium, a static one, not changing. So now we are going to speak a bit more about simulations. Well, actually, we are only going to speak about this anymore. So the rest of the day is simulations. So we have to speak about dynamics, because in economics, there's not really dynamics in those models. It's purely static equilibrium models. Okay, but I will just say one word before about dynamics in economics, because there is still some theory in economics about dynamics, but they don't really study it in the models, but I will still tell you. So how are you supposed to reach an equilibrium in economics? Well, the theory says that you do what they call a tâtonnement process. So it's a French word because it was developed by a French economist, Léon Walras, at the beginning of the 20th century. So it's a trial and error process. So he developed what he calls this Walrasian auction, what was later called the Walrasian auction. So it explains the dynamics of price actually. Where demand is high, price increases, and where demand is low, price decreases. That's quite simple actually. So price is the variable which allows demand and supply to meet, if you want. Is it clear? So that's the whole, quite simplified, but the whole economic theory. But this theory doesn't really tell you what happens for residential moves, because of course we have also residential moves in our models. We have people moving houses and also prices changing. So we need to do both. Well, the economic theory doesn't really tell you what happens for residential moves, but you can go back to the open city model, where you have a growth process. If you start from if you remember the slides I showed before, so you have this empty bucket with a very high utility, and then there's the utility in the rest of the world, which is much lower, so people want to move in the city, and there's an infinite supply of people, so people will move in the city, increasingly, until utility levels meet. Okay, this happens between the city and the outside, but it could also happen within the city if the utility is not the same everywhere. So people would move to increase their utility. So with the price dynamics and this kind of dynamics for moves, you can try to build the model. So, and of course, this is a growth process of an open city, but it could be, of course, also a shrinking process. If the utility in the city was higher than in the rest of the world, people would want to move to the rest of the world, and then you would end up again with the same utility level and another population size in the city. Okay, so this, and so price dynamics make it so that demand and supply meet. So when demand is high, price is increasing. Demand is low, price is decreasing. And for residential moves, it's governed by utility. So when utility is low, people want to move in there. Where utility is, the contrary. When utility is high, people want to move in. Where utility is low, people want to move out. Okay, so this is the kind of dynamics which I used to develop a closed city model, which you will be able to use developed in NetLogo. How much time do we still have before break? Okay, so we can go into this now. Okay, so I'm going to present you this model in a bit more detail. So it's a NetLogo model. You have a two-dimensional grid, as usual in NetLogo, and cells have two possible states. Either they are used for agriculture or for housing. So there can be one or several people living in each cell. So agriculture is represented by an agricultural rent, RA, as we had before in the model. There's a punctual CBD, which is here a black cross on the pictures. And I chose just to initialize the model at random. So you place every agent at random on the space, and the price is just the agricultural rent everywhere in the beginning. There's a quite important feature. I don't know if you remember this formula, but at some point you computed with your star the optimal surface which an agent can have given its distance to the center and the price of the considered cell, R. And this optimal surface is just like this. So it's beta. Beta was the preference for housing surface in the utility function times income minus transport cost divided by the price. Okay. So this is, let's say each agent knows his or her utility and can choose the optimal surface, housing surface because of this. So knowing the price of the cell and the distance to the center, you know which is your optimal surface. And you will, each agent will, at any moment in time, choose this surface according to this formula. Okay? Then with this, you just need to say how agents moves and agents move and prices evolve also. So these are really the dynamics of the model. So it's called, what I used is a standard thing in physics, in applied mathematics, etc. It's called, or in computer science, also it's called asynchronous dynamics. I don't know if you heard about that, or it's not really important. So, well, it's asynchronous by opposition to synchronous. So synchronous dynamics is mostly used for cellular automata. It's like when you have a cellular automaton where you update all cells at the same time. So you look, each cell looks at the state of the neighbors or any other cell and then updates its state. And everything simultaneously. And you can also have models where cells are updating sequentially in a given order. So one cell changes and then the next one changes, but considering the state of the change of state of the previous one. And asynchronous means that you choose the cell which is changing at random at each time step. So on average, every cell is chosen one over the number of cells times per unit time, let's say. So in this case, it's an agent-based model. So there will be agents moving between cells. It's a bit more complex than a cellular automaton. So you choose an agent and a cell at each time step, and both of them at random among all agents and all cells. Okay, and then you will propose. So this ensures that you will choose all agents and all cells after some time, but randomly. Is it okay? Yeah. So and then you propose to the agent that to move in this cell. how does the agent know if he or she wants to move? Then he has to compute the utility. So he knows his current utility, and he computes the utility he would get in the new cell. So, well, I didn't show how to compute the utility, but using the surface and the rest of the formulas you had before, you can compute it. So the agent computes how much utility he would get in the new cell, compares it with the current utility, so he can compute the difference in utility, and if he gains some utility by moving, then he will move. But for this, he has to propose a bid to increase the price of the cell of destination. So, and the bid has this simple form. The increased rent at the next iteration, n+1, is the previous one at iteration n, multiplied by a factor which is bigger than 1. So 1 plus, this is the relative gain in utility. So utility before minus, utility after the move minus utility before over utility before. Okay, changing utility over utility. And then we need to add a parameter here, epsilon. I call it epsilon to control how fast or how slowly prices evolve. Okay. So this says how prices increase in the model. As everything is random, I mean all moves are random, there are some places where prices are increasing really a lot, too much compared to the equilibrium, so they will need to decrease also. So when demand is high, actually when people want to move in some place, then the rent will increase according to this tâtonnement, trial and error process, which I described before. But when cells are vacant, their price decreases. So when demand is low, price is decreasing. So I just chose to have the price decrease exponentially. It decreases by a fixed factor at each time step. Is that clear? And this is also ruled by another parameter. So there are two parameters additional to the ones we saw before for the dynamics. We had just a static model before, now we have the dynamics, and we have added two parameters. This epsilon, so a big parameter, and this TP, so the time is actually the characteristic time of decrease of the price for vacant cells. Please ask some questions. Anything? No. Come on. No? It's not? No? Okay, so I'll go on. So then I'll show you what happens with two income groups. So you have poor agents in red and rich ones in blue, and rich ones have a higher income. I just chose some factor. And you see on the pictures how the system evolves as a function of what I call N, the average number of moves per agents since initialization. So since we are choosing agents randomly, you will have to have an average number of moves per agent. So it's kind of the time, evolving time. And you see that with evolving time, you come closer to some kind of equilibrium. So which I will describe a bit further. And there's an important parameter which indicates you what is the proximity to equilibrium. It's this, what I call delta U max. So it's the maximum relative variation in utility in the system. So you can imagine when you initialize the system, all agents are placed at random and prices are just the aggregate rent. So people have very different utilities in the system. People who end up being very far from the center have a very low utility. People very close to the center have a very high utility. And then people start to moving closer, and the utilities become more and more homogeneous in the system. And so the differences end up being very small in the end. So when they are small enough, I took an arbitrary number of 10 to the minus 6, so the homogeneity of the utility is very, very big. Then I stopped the simulation. So it decreased by 5 orders of magnitude from 10 to the minus 1 to 10 to the minus 6. Okay. So it's a bit the same as what we saw for the open city model. So the utility of the rest of the world and the utility of the city, they become equal at equilibrium. So it's exactly the same thing happening, but inside the city. So all the utility is homogeneous at the equilibrium. And if you remember in the equations which Justin showed, there was only one utility level. So that's one result, an important level. The result, the utility is exactly the same everywhere. Okay? Well, exactly the same, now it will be up to numerical errors, because we are dealing with numbers now, and it's almost exactly the same up to a very small factor. Okay? Yeah? So then I just show you I'm using 2 fingers. I just show you how the things evolve. On the left you have the CT, the simulation space, and on the right you have the price curve. So rent as a function of the distance to the center, and the agricultural rent is 10 is here. So all the prices are 10 at the beginning, and then you see how things evolve. So 1 move per agent on average. People start to concentrate in the middle. 4 moves. 22. I didn't say, but the gray cells are the ones where both rich and poor agents are collocated. Yes. And then after a number of moves, we reach some kind of equilibrium. Yes, please?
On the circle, the red are the poor people and the blue are the rich, basically.
Yes.
But for example, how do you adapt that in reality? Because in France, for example, it's often the rich people in the center and the poor people outside.
Yes, good remark. Yeah. So this is the standard result of this model. When you have 2 income groups, you end up having all low-income people in the center and high-income people in the periphery. And this is supposed to be what happens in North American city, where this theory was developed. So they are happy with this model, because it works very well for North American city. You tend to have a low-income CBD, and then rich peri-urban areas with larger houses, etc. This is true especially for the most recent North American cities, but for cities like New York, Chicago, Boston, it's not really like this. It's more like the European way you were describing, with a rich center and a poor periphery. So in the literature, people mention a kind of opposition between North American and European cities.
And do you think you can find parameters that could adapt for circumstances or?
Yeah. Well, actually, I propose one explanation. In the model you are going to use the next, there's a possibility to do that. It's not really satisfying in my view. From a modeling perspective, but there's a lot of literature on this. There are many papers dealing with this question. People have proposed a number of hypotheses to explain this difference between North American and European cities. People have spoken about the value of time, which would be higher for high-income people, and which tend to let them decrease or they would want to move closer to the center because they value their time highly and they don't want to commute too long. People have also spoken about the center of European cities are very attractive, so there are some amenities to which rich people might be especially sensitive and would want to value, etc.
So it's kind of the case because you say that the utility is homogeneous.
Yes.
For city center, for example, the cells itself has a, let's say, constant utility, if you see what I mean. So that's why maybe it's more attractive. So people with higher income.
Oh no, the fact that there's a constant utility is really because of what Justin explained. So the people choose between, they have a basket of goods, so they choose between this housing surface and the composite good. So people are equally happy everywhere because some people in the very center have a very small housing surface. So this is the rent, but let me go to the next slide and I will be able to explain this in more detail. Well, let me go here. So this is this is rent. Oh yeah, this is density, sorry, next slide, yeah. So this is the density curve as a function of the distance to the center. So people in the very center have a very small housing surface, but they don't have to commute, they can go by foot. So they are happy because of that. They compensate the high price they pay on housing by low commutes. And so all in all, they are equally happy with the utility function we chose. People a bit further away, they have to commute more, but they have a higher, larger housing. So that's the trade-off. Okay? Yes?
All these agents, they are different. They behave differently, or like?
They just have the behavior I spoke of before. So they move to increase their utility, which is the same for everyone. And the prices, they just evolve like I told you. The vacant cells have prices which decrease. The people move and they have to bid on the new cell to make the price a bit higher.
Okay.
So it's just the whole behavior, I described it to you, so there's nothing hidden. Okay. So what I wanted to say actually with this slide is that the equilibrium which we reach with this agent-based model is exactly the analytical, or almost exactly the analytical one. So the analytical one is the continuous lines, and the agent-based model is given by the symbols. And well, you see that they fit very well. The main difference is that the analytical model is continuous. You have a continuum of households, and you have a discrete number in the simulations, of course. And so you see it, especially here, there's a discrete number of people per cell. So here you have 10, 9, 8, etc. So it's like a step function. You see it very clearly in the end. And you will see it even more clearly on the simulations, because here I had many agents because I wanted it to look good. But it takes a long time to run, so in the simulations I put well, you can change it of course, but the population size will be much smaller, and you will see this effect more clearly. Okay, so there's a drop here, which is also, it happens for both models. It's because here you have low-income households, they have a small housing surface, and then you jump at the same distance to high-income households, so they have a bigger housing surface, and this changes the density suddenly. So it's really because of this difference in income. Okay. So this was just to say that this is what we find as an equilibrium is really the analytical equilibrium. So it works also for the rent curve. So they are. I should mention this is important that well, actually I can use this thing a bit more. Okay, there's this point here where the rent curves connect. So because of this competition, just like at the outskirts of the city, the competition between housing and agriculture makes the agricultural rent and the rent at the fringe of the city equal. You have an equal rent between the two income groups. Okay, but there is here a jump of the housing surfaces. So this is just the inverse of the density function. Okay, so now you have you have just an agent-based model which finds the equilibrium of the analytical model we described before. So the way I've been using it is just to the way we used actually simulations in physics. They are usually used to study phenomena which are difficult to deal with analytically. So in our case here, it's for instance looking at the polycentric city, so with several centers it's more difficult to solve than with just one. The social spatial structure, so this question of location of income groups, etc. Okay, so I think now you should use the model yourself. So it's available on the Moodle page. But since it's already 20 past 12, maybe we should go for lunch and then do it afterwards. So, makes sense? Yeah, so let's do it after lunch. Yes, if you have questions, sorry, maybe. 2 more minutes. Just one here. Sorry, just some questions. In English, maybe louder, is it possible?
Louder.
Aussi, c'est différent paramètres made.
What is utility made of?
What is utility made of?
In your own
What is the paramètre?
Oh, I didn't. I didn't say it, but the utility is exactly the function we studied from the beginning with Justin. So it's exactly the same utility. It's supposed to give exactly the same results, and it gives the same results as the one which Justin showed you before. So yeah, utility function, budget constraint, everything is coherent here. It's all the same as what Justin presented. It's the basic Alonso model. Using this utility we have been using is called log linear. There are many forms. It's called log linear. It's the same as maybe you heard of one which is called Cobb-Douglas. It's the same. It's quite famous. There was another question, yeah?
Thank you very much for your presentation. And my question is, I can see you're choosing one parameter one at a time to make the analysis very clear and to do comparison. And my question is, in the urban context, sometimes two parameters can emerge near meaning. And have you considered how to, like, what information you're missing out?
Yes, you mean when we do the comparative statics or when we do this sensitivity analysis, we are changing one parameter at a time, or is it?
I think it's both, because using like the agent-based and the CA connection, when you're using agent-based with CA, you're also changing one parameter at a time to study one parameter at a time.
Oh, well, what should I say? Well, the way you will see, we will change the two parameters actually, which are coming from the dynamics. We are going to do it just now actually with looking at their influence. You will be able to change them both together. So there are only two. So that's a simple case because you have not too much simulations to do to change two parameters at a time. But for the other parameters of the model. As I showed you, you just get the analytical results. There was a very good agreement between analytics and numerics here. So actually, you don't really need to explore the parameter space because it gives you the same as the mathematical model. So you already know the mathematical results. You can check if you want for other parameters that it's also in agreement with the mathematical model, but there's not much use. As long as it's in agreement with the mathematical model, then you know what it's going to do. Because this model is really well known, there has been tons of papers on it, so you don't really need to explore it. You can if you want, but you already know what results it's going to give you. Is it okay? Yeah? Other questions? Okay, so bon appétit.